Welcome to lesson 4 of our 5th unit, relating polynomial functions and equations. So if you can recall characteristics of a quadratic function, we had a couple of things that we could derive based on the format of our equation. So when it was in standard form, again for quadratics, meaning to the power of 2. When it was in standard form, written out as squared x and a constant, our y-intercept was always given by the constant. When we then kind of factored it out into vertex form, then we were able to learn its vertex or its minimum maximum. We could also learn about the x-intercepts if we were able to actually straight up factor it. So in general, quadratics could be used to identify all of these different things, and they're the characteristics that we look for in pretty much any graph. So in terms of graphing, things you can look for are things like vertex, axis of symmetry, y-intercept, and x-intercept. So you can do this by creating a table of values or using Desmos, as we did in our previous lesson. But you can create a graph of the quadratic function that's given, and then you can determine the vertex, the maximum or minimum value, the y-intercept and the x-intercepts, and the domain and range. So for this particular one, and some of this information we can glean from this, again, y-intercept is going to be at -3. It's going to be opening upwards because of my coefficient attached to x squared. But beyond that, I can't really tell much from this shape. But if I do factor it, then these are actually my x-intercepts when y equals 0. So I'm looking at x equals +3 and x equals -1. My minimum should be here. That's going to be at -4. Again, really working to make sure that that's curved, not a V. And that would be my sketch. Okay, so factoring is another method that we can use. So again, algebraically, that's one thing that can help me. But all of those key things can come from details here. Y-intercept, opening upward. X-intercepts, always changing the sign from the factored version. So now I can actually answer the question for all the characteristics of this graph. My vertex, if I could spell it correctly, that would be helpful, will be at +1 and -4. And again, you could determine that because the vertex should be halfway between your intercepts and then just plugging in 1 for x in your original equation to solve for y. It is a minimum because it's opening upward at y equals -4. My y-intercept, again, is coming from my original equation at -3. My x-intercepts are x equals 3 and -1. My domain for all quadratics is positive to negative infinity, or negative to positive infinity, always starting at the lowest and going to highest. And my range, since I said it was a minimum, is going to start at -4 and open upward forever. So that's all quadratics, and that's great. That's grade 11. Polynomial functions, we can then generalize for a wider variety of exponents attached to x. So the highest degree that's in our polynomial is the highest exponent attached to our variable. So that's what we see here, degree n, and again, n is the highest, and each term after it should decrease technically by 1 based on our binomial expansion theorem. Okay, where we will have a coefficient attached to every one of these x terms, and n itself just refers to the term number. So this looks like a lot of math jargon, but really what it means is you can write any polynomial for any power, and it should be able to tell us a little bit about what we're looking for in terms of graphing characteristics. So degree of 1 means that we're dealing with a linear polynomial, which means it's an odd degree. So again, we kind of threw out this idea yesterday of odd versus even. Odd meaning that they go diagonally between quadrants, and even being that they end behavior goes into the same direction, either upward or downward. So what does that look like? Well, for linear, that would be something, or most simplified version is y equals x. And when we have a positive leading coefficient, so it's positive, the slope of my graph is going upward. So if I was graphing it, it would go like this, which means that I'm going from quadrant 1 or quadrant 3 to quadrant 1. If I were to graph it with a negative leading coefficient, when we talked about slope in grade 10, that meant that it was going downward like this, which means I'm going from quadrant 2 to quadrant 4. And again, always reading from left to right. When we talk about even exponents, it's an even degree, like a quadratic, our most basic version being x squared. When we go to graph these, they point in the same direction at both ends. So with a positive leading coefficient, that's just like plain old x squared, I would expect my ends to be in quadrant 2 and quadrant 1. But with a negative leading coefficient, it flips my parabola over, meaning that it opens downward. And both ends are still pointing in the same direction, but this time they're pointing down, so pointing at quadrants 3 and quadrant 4. In general, what does this mean? Well, it means, and we find this applies even with higher degrees, is that if we have an odd degree for a polynomial, we expect it to be a somewhat diagonal shape. So our ends point at diagonal quadrants. Whereas even degrees, whether it's 2, 4, 6, 8, 100, we would expect our final end behavior to be pointing in the same direction, either upward or downward. So quadrants 2 and 1, or quadrants 3 and 4. We see this carry through if we were to start graphing like y equals x cubed. If you go in onto your graphing, onto Desmos, you'll see that the general shape looks something like this. Again, we see that we go from left being quadrant 3 to right being quadrant 1. Our negative coefficient out in front of this causes that vertical transformation or flip, resulting in a shape that looks somewhat like this. Again, then pointing at quadrant 2 and quadrant 4. So even though there is a curve to this shape now, unlike our linear equation, we're still kind of somewhat diagonally passing through that origin or across my coordinate plane. Cortex would be looking at like y equals x to the 4. This isn't something we really have done, so I'm going to pull up decimals so you can see what it looks like. You can see that just because I'm dealing with a quartic doesn't mean, sorry, don't know why it's jumping around like that, that it's changed my end behavior, but in actuality it's still, my ends are still both pointing upward, and it looks kind of just like a flattened parabola. So when I go in here and fill in my notes, that's exactly what I would draw. I would draw kind of a flattened out parabola. That impact of a negative out in front, and if we go back into decimals for a second, I can show you, simply flips it over so it's pointing downward. So we see the same trend as when we were dealing with our quadratic. That our ends and behavior of even functions, or even degrees rather, point in the same direction. So quadrant 2 to quadrant 1 versus quadrant 3 to quadrant 4. Okay. We can carry this on for quintics. Again, I'll go into decimals here so we can see. If we put it to the power of 5, and I'm going to get rid of that negative that I had, we get, again, that same curvy, diagonal-ish shape that we got with r cubic. So when we go in, we see this shape, and conversely, when we threw that negative in there, we simply got the reflection over that x-axis. So again, we go from quadrant 3 to quadrant 1 versus quadrant 2 to quadrant 4. In general, we can then use this end behavior to our advantage and state that when we have an odd degree polynomial function and a positive leading coefficient as x approaches positive infinity or goes to the right, the graph rises. As x approaches negative infinity, aka going to the left, the graph falls. The negative version of this is the opposite. And this is for odd degree polynomial functions. Even degree polynomial functions do the same thing on both sides. So when we have a positive coefficient, a positive number out in front of that highest degree variable, we're looking at, as we go to the right, the graph rises. As we go to the left, the graph rises. If we have a negative out in front of that highest degree, then our graph will fall both to the left and to the right. So that's the first principle we can use. We can know the general direction that our graph is going to be going. The next thing that we want to be able to find out is where are the x-intercepts, or also known as the zeros, of the graph. And we do this by factoring, just like I did in that quadratic example. X-intercepts, we see them called zeros, and we do this by factoring. And we already know how to factor a polynomial because we did that in lessons like 1 and 2 technically. And so we can kind of play around with using that math to help us now. So when a polynomial is fully factored, it makes life a lot easier because we can identify our zeros right away. they would be positive 1, remember opposite sides, positive 2, negative 3, and negative 1. So opposite signs of our factors. Now it says complete a sign diagram to help with the graph. What that means is if we created our number line and we looked at what's happening between them. We've got 4 zeros, so I'm going to put them in order. Negative 3, negative 1, positive 1, and 2. Okay. Then I'm going to look at it and say, okay, well, what would be happening over here if my x value was less than negative 3? So if it was negative 4 and I plugged it in, what would happen here? So negative 4 minus 1 is negative 5. Negative 4 minus 2 is negative 7. Oops. Negative 6. Negative 4 plus 3 is negative 1. Negative 4 plus 1 is negative 3. If I look at these values, I see a negative times a negative times a negative times a negative. 4 negatives multiplying together, which means that overall I can expect my graph to have a positive value here. I don't even actually need to finish evaluating it. I don't need that coordinate point. I just need to know what to expect. I would expect positive values left of negative 3. In between them, I would have negative 2. So if I plugged in x equals negative 2, then I would get negative 2 minus 1 is negative 3. Negative 2 minus 2 is negative 4. Negative 2 plus 3 is 1. And negative 2 plus 1 is negative 1. Here I have negative times a negative times a positive times a negative. 3 negatives, which overall would give me a negative value. Over here I can use x equals 0. So that would be negative 1 times negative 2 times 3 times 1. That'll gives me a positive value. So I'd expect to be above the x-axis. And finally in here, like 1.5 doesn't give us the nicest numbers, but 1.5 minus 1 would still be positive. 1.5 minus 2 would be negative. 1.5 plus 3 would be positive. 1.5 plus 1 would be positive. So overall, I would expect this to have a negative result. So I don't even actually need to put the numbers in here. As long as I look at the signs and see what kind of product they would give me, I can then predict where my graph would be. And then finally, I need to figure out on the outside of 2. So I could use positive 3, in which case positive 3 minus 1 would be a positive number. Positive 3 minus 2 would still be positive. And then these last two have to be positive because they're adding to an already positive number. So I'd expect a positive value over here. Again, this sign diagram is what this is called, and it lets me predict where my graph should be, above or below the x-axis. So when I look at this, I see, okay, well, I need to, first of all, put my information in here. Label these. I'm not going to put values on my y-axis because I don't actually have any coordinates. But I know my zeros are at positive 1, positive 2, negative 1, and negative 3. So I know that those points are defined. I know my graph should be above the line here, and it should be below here. but it should come back up, go back down, and then rise again. So again, that anytime I see a positive in my sign diagram, when I go to actually sketch my graph, it's above my x-axis. When I have a negative for my sign diagram, I would expect my graph to be below the x-axis. Now we can check our answer using decimals, and that's exactly what I'm going to do. So give me a second and I'll pull that up. As you can see, I have the correct general shape. I've got that W effect. Both my ends are pointing upward, which makes sense because I had 4 x's. So if I had multiplied that out, this would have been an even degree polynomial. And I even have that kind of effect of my one local minimum, or my one valley is lower than my other one. And again, this is why I don't label my y-axis, because I don't have any specific values. And so I'm not wrong in drawing this, I just haven't labeled how far below it's gone. Okay, so that's what we're seeing. So again, end behavior pointing upward in the same direction because there's an even number of x's, an even degree, and in terms of upwards, not downwards, because of how everything panned out and doing that sign diagram to ensure that I've got it pointed in the right direction. You can find the y-intercept and graph it. So that was a flaw in this graph, is that I didn't find the y-intercept. I sketched it strictly from my sign diagram. Okay. D, find where the graph changes from increasing to decreasing is called a local maximum point. The y value of this point is greater than those of the neighboring points. The local minimum is where the y value is lower than those of its neighboring points. So that's where we see these kind of curves. We've got a local max, and these are both local minimums. The maximum number of intercepts that any polynomial can have is the same as the degree that it has. So when I look at this one, I've got 4 x's. If I multiplied this out, my degree would be x to the 4. And I have 4 zeros. That's the most zeros I could have. I could have less, I could have fewer, in which case we would end up with what's called multiplicity. But 4 is the number of zeros we would expect. We would also expect the number of maximum and minimum points to cap out at 1 less than what we have. So again, if we go back, we have 1 maximum and 2 minimums. That's both lower than our degree. So that fits. The graph of a polynomial function is smooth and continuous, which means it has no sharp corners. That would be my one issue with this graph, is that how wobbly it is. Okay, you would want to try and smooth that out. So let's try doing this entire example where we can graph this polynomial. So again, I'm looking for my y-intercept, I'm looking for zeros, I'm looking at end behavior. I'm also looking at which kind of parts of my graph are above and below the line, and local maximum and local minimum. So starting with end behavior. I look at my highest degree term, and there's no coefficient, which means the coefficient is 1. It's positive. That means that from left to right, I'm going from quadrant 3 to quadrant 1 because it's an odd degree polynomial. So I already know this is kind of what I'm expecting. Then I can look at my y-intercepts based on the format that it's in. Well, I would need to look at my constant for me to be able to do that. There is no constant, which means that my y-intercept is 0. Now that I've isolated those kind of key pieces, I'm going to look for, okay, well, what else can I learn about my graph? I'll start with my x-intercepts, or my zeros. And again, I do that by factoring. So I'm just going to rewrite it so I don't have any major glaring errors right off the hop. So the first thing I always look for when I factor is a greatest common factor. So I look at all three terms in this particular case, and I notice that they all include x. So I can factor out an x. That leaves me with the following quadratic in brackets. I can't drop that x because otherwise I would lose my cubic characteristics, but I can factor this further. And once it's completely factored, as it is here, now I can note that my zeros are going to be where x equals 0, -3, and 2. Once I have my zeros and I know my predicted end behavior, I can kind of guesstimate what things might look like. At this point, you are totally welcome to also do a sign diagram. Okay. But I can already predict my end behaviors are going to look like this because of that positive value and the fact that it's an odd degree. So the question is, what do I look like in here? What am I looking at? So that's where part 4 comes in, looking at my local maximums and minimums. So I can actually just calculate some values. So I'm going to look at -2, -1, and 1 to kind of help me out. I'm going to do that by literally just plugging into my original equation. So that would be -2 cubed plus -2 squared minus 6 times -2, which would be -8 plus 4 plus 12 over +8. Each of -1 would be -1 cubed plus -1 squared minus 6 times -1, which would be -1 plus 1 plus 6, which is 6, and 1 cubed plus 1 squared minus 6 times 1 would be 2 minus 6 is -4. Now that I have those values, I can predict approximately where my local maximum might be, where my local minimum might be, and kind of scale it appropriately. So I might say 8 is here, and -4 is about half as far. So when I go to graph this, I'm going to try and go through those points. And that would be my graph. So that's my sketch of the following, of the equation x cubed plus x squared minus 6x. So I go back and I make sure that it's smooth and continuous. Did that relatively. I might fix this part up a little bit if I was using. Make sure that that's all nice and rounded. This is smooth. Move this part out in here. Okay, just to make sure that that curve is nice and clean. If I was using a pencil, I would erase and redraw multiple times. But that allows me to create that graph. And if you wanted to check, you again can always use Desmos. So if I type in my equation here, y equals x to the power of 3 plus x squared minus 6x. We see that that's pretty much what we get. I might have been a little bit off in terms of where my max and min were. It's a little bit right of 1. It's a little bit right of -2. But we're not far off. So using those 4 characteristics and then the idea that we need to smooth our curve out really allows us to get a pretty good picture of what our curve might look like without creating this massive table of values. So if you want to pause this at this point and at least try and to start defining some of these characteristics, again, the 4 that you're going to really want to identify, and it doesn't need to be in this order, would be end behavior, y-intercept, x-intercept, and local max and min. So again, if you want to pause and give it a shot on your own, do that. If you want to follow along, I will continue talking. So again, I'm going to start with end behavior because it's just, for me, the most obvious one. Because I look at my degree and it's even. That tells me it's opening in the same direction. And then I see that my coefficient with that highest degree variable term is positive. So that specifically means that it's opening upward. Again, spelling does not seem to be my forte today. Y-intercept is pretty straightforward when it's in this format because again it's all multiplied out, so I strictly have to look at my constant term. It's -6. It only starts to become tricky then with my x-intercepts, because now I need to start factoring this. So I'm going to use synthetic division. You could always use remainder theorem. You could use long division if you really want. Whichever kind of makes the most sense to you. I just like synthetic division because I find it the quickest. So again, I always look at my constant to decide what are my possible options. So I could have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6 are my options. So start with 6 maybe this time, positive 6. I fill in my coefficients, 2, -1, -14, 19, -6. Carry the first one down, 12, 11, 66. This is not looking good already. It does not look like it's going to get to 0 at any point in time soon. So I'm going to try maybe -6. 6s seem like they'll just leave me in bad places. The number seems like they're getting too big. So maybe try positive 3. 2 minus 1. Carry the 2 down. 6. 5. 15. 1. 3. 16. Okay, that one is closer. Maybe negative 3 would work better instead. Negative 6 is negative 7. 21 leaves me with positive 7. Negative 21 leaves me with negative 2, positive 6, 0. Perfect. Okay, so again, I could eliminate that 6 because it didn't seem like it wanted to be anywhere near giving me a 0 remainder, whereas the 3 seemed like it was going to give me at least somewhat close of a remainder. These numbers all seemed to be within reason, so that's why I opted to try the negative 3. That means that x equals negative 3 is one of my x-intercepts. And one of my factors then is going to be x plus 3, because remember we changed the sign. But now I have another polynomial that I need to work with, remembering that this is x cubed minus 7x squared plus 7x minus 2. And I still don't see a factor from there, so I'm going to need to try and pull some factors and use synthetic division again. So my options here are plus or minus 1 and plus or minus 2, and that's it. So luckily I've got something to work with here. A little bit less to work with though, so it makes my life a little easier. And so that's what I'm going to try. I'm going to try positive 2. 2, negative 7, 7, and negative 2. Shorter so I don't take as much room. Carry the 2 down. 4, 6, 1, 2, 0. And it works! Yay! So I've got another factor now. I've got x equals 2, or x minus 2 is another one of my factors. From here, my remaining polynomial is a quadratic. And this is factorable. So knowing that, I am going to simply factor it out. This would factor to be 2x minus 1 times x minus 1, meaning that my other zeros, or all my zeros altogether, are negative 3, positive 2, positive 1/2, and positive 1. Once I know those, I can create my sign diagram to know where my graph is kind of going. And I can already sketch out most of it here. So again, I know my y-intercept is at negative 6, but I don't know where that is relative to everything else, so I may not draw that yet. But I know I need to end going upward on both sides, and I know my zeros, again, are negative 3, 2, 1, and 1/2. So, negative 3, a half, 1, and 2. Again, my end behaviors should be pointing upward. I know that down here should be going through negative 6, wherever that is, but I still need to figure out where my minimum is. I should have some sort of local maximum in here, and then a minimum in here. in order to be able to end up going back up. Again, you can totally do a sign diagram to help yourself with that. What that would look like would be is me checking some values in here and plugging them in. At this point, if I wanted to do a sign diagram, I would probably work with my factored version of this equation though. And so that's where I would go back to what I had here, x plus 3, x minus 2, and then these two pieces down here. Okay, because then it's just easier to decide on signs. So if I was going to do sign diagram, I'd have my -3. This one, because it's just for my own personal reference, I don't need to worry about spacing. I just put my numbers on it, and then I can predict. So if I put in -4, I do -4 plus 3 is a negative. -4 minus 2 is a negative. -4 minus 1 is a negative. And -4 times 2 is -8 minus 1. Still a negative. So overall, that should be positive. 4 negatives equals a positive, because 2 and 2. Okay. I would use 0 here, just kind of as a tester. I know it's -6, so it should be below the x-axis. In here, you're dealing with like 3/4 plus 3 is going to be positive. 3/4 minus 2 is going to be negative. 3/4 minus 1 is going to be negative, bigger. 6/4 or 1.5 minus 1 is going to be positive. So overall, this creates a positive product because those two negatives cancel out. Between 1 and 2, so 1.5 plus 3 is positive. 1.5 minus 2 is going to be negative. 1.5 minus 1 is going to be positive. 1.5 times 2 is 3 minus 1 is going to be positive as well. So this whole thing is negative. And then 3 plus 3 is 6, so that's positive. 3 minus 2 is going to stay positive. 3 minus 1 is going to be positive, and 6 minus 1 is going to be positive as well. So above the graph there. And so again, we're kind of already seeing from that sign diagram where things should be. So again, positives we would expect to be up here. And we have that on our end behavior, so we're on the right track. And negatives we would expect to be below our x-axis. Okay. So now it's just a matter of how high and how low do we go. So we need to test some specific values in here. So I would maybe try x equals 2, x equals 1, x equals 0 we already know. Then we would try that quarter and actually plug it in, like 1.5 and plug it in. So for those ones we would probably want to use a calculator. So if you want to do that right now, I know you can plug and chug. I don't need to do that for you. So when you work it out, again, I used my factored form to kind of expedite the process instead of having to deal with to the power of 4 if I didn't have to. I'm able to identify that my local minimum is probably going to be pretty darn low and close to -2 here. So put it way down there because it's way -60. 1 is about halfway, 6 is like way up here. Okay, so in terms of like sketching that out, that's what that's going to kind of look like. It's going to be a pretty sharp angle downward and then curving up. It barely goes above here, so I got to be really conscious of making that nice smooth curve. again. There, and then it barely goes below when it comes under here, so that's going to be a really smooth, rounded curve there also. And so that's going to be my final graph. So it's a little tricky, I know, but using those sign diagrams is really, really helpful. And then using your ability to kind of predict where things go and your arithmetic to solve for those different values is going to be really, really helpful. So finally, we get to multiplicity of 0. This is kind of a tricky one, but they're our last two examples. So just looking for basically when you get the same factor more than once. So what happens when we have multiple roots that are the same? Well, we'd expect a similar shape to if we were just looking at that function. So we see this in what we're talking about right here in our notes. So when we have this multiplicity of 2, we expect to see kind of a parabolic shape or parabola when we graph it. So that idea that it comes to the graph and just kind of bounces off and doesn't actually pass through my x-axis. And so that's the key idea. We would say multiplicity of 2 would be like a parabola. And so it bounces off. The x-axis. When we're dealing with a cubic, like we have here, we would say that the multiplicity is 3, because that's the exponent. So multiplicity is just the exponent, or how many times that 1 0 shows up. And we would expect to see a cubic shape where it kind of curves through the graph instead of just curves through that x-axis instead of just passing straight through in more of a straight line. So kind of this cubic behavior. Okay. So we're seeing this behavior at 0 in this particular case, but this rule still applies when we look at any other polynomial that has a multiplicity. So even multiplicities, we're going to expect a parabolic sort of effect, and odd, we would expect sort of the cubic effect. So what we see when we graph this, and I can show you quite quickly if we use Desmos. Oops, apparently that disappeared. Is we've got x minus 1 to the power of 4 and x minus 2. And when we zoom in on that x minus 1, we get that to the power of 4 sort of bouncing off of the 1 and coming back down instead of passing through. Okay, so and again, with a to the power of 4, it's flatter than a parabola. So that's why it kind of looks like it totally pancakes out there. Whereas we have a multiplicity of 1 with that x minus 1, and so it just kind of passes through, no distinct shape. So when we go to graph something like that, that's what we need to keep in mind. In addition to all of that, so we would show 1 and 2, because those are kind of important points. Oops, I typed it in wrong. Should be -1. Let's see what that looks like. There we go. That's better. So you truly get a better sense of that plateau at -1. And then it comes back down and passes straight through at 2. That looks better. Okay. So when I go to sketch it, I would want to emphasize that shape. Again, trying to make it as smooth as possible. And coming up here. And that would be my general sketch of my graph. So -1 and 2. From my intercepts. Now, overall, this has a degree of 4 + 1. So a degree of 5 means that my ends should be pointing in opposite directions, which they are. My x's are all positive, so I should go from quadrant 1 or quadrant 3 to quadrant 1, which I do. Okay, it's just that kind of interesting shape that we get forming around that repeated 0. That is kind of the unique part of this. So even though it has technically that, for lack of a better word, kind of cubic shape, we would expect it to go much lower here because it's actually to the power of 5, whereas a cubic might only like dip down to about here. So all the features are kind of exaggerated. Okay, so that's kind of the key idea there. Now we would also want to find like our intercept and our local minimum. So those would be values that you would plug in, but for the sake of the fact that our video is already quite long, and we've got a couple more examples where we can play with that, we'll skip ahead. Well, we've got one more example. So we've got example 2, looking at multiplicity. I'm going to expect some cubic behavior around this 0 and some, again, just passing straight through around this 0 here. But I'm still going to do like my whole analysis for this one. So I'd start with my end behavior. And I look at 3 + 1 is 4, so they should be pointing in the same direction. Because it's to the 4th degree. And with this negative out in front, that tells me that it's going to be opening downward. Then I can look at my y-intercept. And this I would have to solve for. So I'd have to multiply this all out. So I'm going to pause the video so I can just do it. I suggest you practice multiplying out your factors here. So once you've multiplied it out, you should have, specifically looking for that constant term for my y-intercept. So my y-intercept will be y = 3. My zeros, based on the factored form that I was given, are going to be at x = -1, but I'm going to note that this should be a cubic shape, and x = +3. So then the last part I can do is deciding kind of what my graph looks like, making that smooth curve. So again, -1 being here, 1, 2, 3, here. Okay, I'm expecting my graph to eventually open downward. But what's going to happen is that it's all actually going to be not a parabola, but I'm not going to cross my x-axis again until I'm going downward at my other end behavior. So again, I curved in towards 1 like this because I'm expecting that cubic behavior. Now, I'd need to find some more values up here to be able to decide like where my maximum is. I know that when x equals 0, y equals 3, but I'm going to test out those other two, and you can do the same. So when I solve for these values, I go from 3 to 16 to 64. So I'm going to assume that this is my maximum. And I'm going to have a really kind of gradual rise here. With that being said, if it's so small on this side, it should be symmetrical over here. So again, that's why I erased this side. So if it's only going up to 3 versus like 64 way up here, it's going to be pretty shallow. This is not a pretty graph. Something like that. Something along those lines. And so that would be my final curve. And again, I would want to maybe mess around with the idea of it being more straight, a little less bumpy. Trying to smooth that out. That's somewhat the product of the pen that I'm using here. Okay, so again, expecting that cubic behavior here while passing straight through that 3. So that's the one thing to watch out for, is multiplicity and that weird behavior. Otherwise, if you don't have any multiplicity, you would get just like what we saw here, where every 0 is a passing through onto the other side of the x-axis. So again, there are some practice questions right here. There's additional practice if you go to this link, and if you have any questions, this is probably the trickiest part of this unit in terms of like putting everything together. That's definitely our longest lesson of this unit. So please don't hesitate to ask questions.